So today we're very happy to have Loseu from Yale University and the IAS. The title of his talk is Parabolic Version of the Two Realizations Theorem and Applications to Modular Representation Theory.
Okay, thank you, Mikey, for having me. I believe that's the final talk on two realizations. And this is on joint paper with Bezrukovnikov. So let me explain a motivation for what we are trying to do. And this motivation comes from modular representation theory, namely a representation theory of semi-simple D algebras. This has to do with character formulas for irreducible representations of this algebra. So Bezrukovnikov and Mirkovich proved a conjecture of Lustig, which identifies the following two things. So first, there is a basis of simple G modules with given P character, and I should also say principal Harish-Chandra character, with the canonical basis in K-theory of the Springer fiber. Conjectural description was also due to Lustig. Now, in general, there is an issue because this basis is too implicit to get any explicit, for example, Kazhdan-Lustig type character formulas for the samples. And so, what we discovered with Roman is that if you are willing to modify the category of representations, well, slightly, let me put quotation mark. And what this means is that instead of looking at just modules of your D algebra, you look at modules which are equivalent with respect to certain reductive subgroup inside of G. And you take equivalence with respect to a group whose connected component is a torus. Okay. So if you are willing to do these modifications, then we still can get Kazhdan-Lustig type character formula for the simple objects, now in the equivalent category. So as usual modules of your D algebra, these guys are not going to be reducibles. They're only reducibles when you consider them as equivalent modules. And connection to what we discussed in previous talks of the series is that when your P character is distinguished, I will later explain what I mean by this, then this character formula that we get will be a case-theoretic consequence of a category equivalence, which will be deduced from a parabolic version of the two realizations. So that's what my story today is about. Okay, and before I, so let me scroll up. There will be two parts. There will be a larger part dealing with the parabolic version and a smaller part dealing with applications to modular representations. So before I get to parabolic version, let me give you a reminder on the two realizations here. So I start with a G, which will be a connected reductive group throughout. Of course, I can consider also the Langland's dual group, G check. And I want two geometric categories. The first one has to do with the Steinberg variety, Steinberg scheme, which is defined like so. So fiber product of G tilde, which is Grothendieck resolution, and N tilde, which is Springer resolution over G. And of course, the group G naturally acts on this entire variety, so we can talk about derived category of equivalent coherent shapes. So that's the first category we consider. Now, we also have a constructible category. Starting from G check, we can get to the loop group, like so. And inside we have Ivachori and its pro-unipotent radical, which will be denoted by I0. And we can form the fine Flach variety, the quotient like so, and consider a derived category of Ivachori constructible shifts, dBi circle of flags. Okay. Then part of the two realization theorem due to Bezrukavnikov tells you that this constructible category is equivalent to the coherent category. And let me give this equivalence a name. It will be called tau. Now, there are two features of this equivalence that are going to be of great importance for this talk. First, this is a bimodular equivalence. So we have two realizations of the affine category, which are monoidal categories, and they act on these two categories. And they also happen to be the same. So first realization is a completed one, which was described in Pablo's talk. So I have coherent shifts on a completed version of Steinberg, and I have completed version of the constructible category as well. Then there is another version which I call specialized. So on the constructible side, this are Ivachora equivariant shifts of them on the affine Flach variety, and on the coherent side, we will have equivariant coherent shifts now on a derived scheme, which is n tilde times n tilde over G. And it turns out that these monoidal categories are equivalent as well to in the corresponding version, and the equivalences again are going to be denoted by tau. Okay. So we have equivalences of monoidal categories and we have equivalences of bimodular categories. Another very important feature is that this equivalence tau from the theorem is nicely compatible with T structures. Namely, it's T exact, where on the constructible category I take the usual perversity structure. But then there is also a perversity structure in the coherent category. And this the heart will be perverse by modules over the non-commutative Springer resolution. And I will elaborate on this later. Are there questions so far? Okay. So let me proceed to the parabolic version of this equivalence. And I start by fixing a parabolic in G. Then I can consider n tilde sub p, which will be the cotangent bundle of G mod p. So before I had G mod b, now it's G mod p. And I can form the corresponding derived Steinberg scheme. Now it's derived when p is different from b. This will be a genuinely derived scheme. And I can still consider derived category of equivalent coherent shifts. On the other hand, starting from p, I can get parabolic in the Langlands dual to be denoted by p chuck. And I can take the corresponding parachoric inside of the Lie group, form the parabolic affine Flach variety for this parachoric, and take the category of Ivachoric constructible shifts on the parabolic affine Flach variety. And then we have the following theorem. I will first go in just to state the most basic version, and then describe the properties of the equivalence. So we have, not surprisingly, we have an equivalence of triangulated categories to be denoted by tau sub p between these two categories. Okay, so when p is equal to b, we just recover the previous theorem of Bezrukavnikov. And what's important is the properties that this equivalence has, which I'm going to list. So first of all, it is compatible with the initial equivalence in a way that we have the following commutative diagram here. So the horizontal arrows are equivalences. So this we know. This is what we want to construct. And then we have natural factors going from the parabolic category to the full category, both in the constructible side here and coherent side here. And these are pretty standard. So let me describe them. So first, let's do the constructible one, which is very easy. We have a projection whose fiber is p check mod b check. And then we can just take a pullback with a shift. So this is symmetric. This is symmetric with respect to duality.
Yeah, a little typo there. It's phi 2.
Oh well. If I declare that my field has one element, would fix it. Never mind. So now on the coherent side, we have a pull push. We have a standard correspondence between n tilde and n tilde p, which is denoted by z here. And well, I take the cotangent fiber for G mod p, but then I take the homogeneous fiber bundle over G mod b. Okay. And this thing includes into n tilde. It projects onto n tilde p. And so I can form the corresponding morphisms between the Steinberg schemes. I take pull push and then a nice little twist with a line bundle to make things work. And I don't want to write this twist explicitly. So when we wrote this paper, various twists were very pleasant as usual. Okay, so I have these two functors, and I want this diagram to commute. That's a very initial requirement. On these categories that I have in my theorem, let me scroll up, I still have action of the completed version of the affine Hecke category. And I want my equivalence, tau sub p, to be equivalent. Just a little remark. You need to twist one of these equivalences with a line bundle. But that's again, let me not get into that. So that's also a very initial requirement. I should be able to compute the image of the most basic object on the constructible side. It's a skyscraper at a point under this equivalence. And it's like this. So I have my Z, this correspondence, which goes both to G tilde and to N tilde P. And so I can consider the diagonal embedding into the Steinberg. So the skyscraper goes to the structure sheaf of this subscheme. Okay, and then, very importantly, I also want T exactness, just as for the initial equivalence. So let me explain the T structure. So on the constructible category, I still take the usual perverse T structure. So that's very standard. Let me explain what's going on the coherent side. That's very similar to what we had for the full version of two realization equivalence. So Bezrukavnikov and Mirkovich constructed the tilting generator E on G tilde, which was prominently featured in Roma's talk. And I can take the non-commutative Springer resolution, which is this algebra A. Okay. Now, using my correspondence, which was called Z, I can pull push E to T star G mod P. Okay, like so. So that's the corresponding pair of maps. That's just reminded here. And Bezrukovnik von Mirkovich also proves that what I get is a tilting generator now for n tilde p. Okay, it's going to be denoted by E sub p. And I take the endomorphisms. All right. By the construction, both these guys are algebras over, well, G or G star. So I can take the tensor product. Okay. I don't need to do anything derived because the first factor is flat over C of G. And finally, my group acts on the algebras like so. Well, just acts on the algebra, so I can consider the category of equivariant modules. And I get a derived equivalence between my initial coherent derived category and the derived category of modules over this algebra. And then I can consider Perversity structure here, as was discussed in Roma's talk. Okay. So I have two Perversity structures, and the claim is that the equivalence that I'm going to construct is going to be T exact with respect to these T structures. Now, it should be pretty clear why I care about property 1 and property 4 in commutative diagram and T exactness. Now, why would we care about 2 and 3 is that they allow us to control what happens with standard objects under this equivalence tau p. So how do we get standard objects? Well, we take the skyscraper and start to apply wall crossing functors. Wall crossing functors constitute a break group action, and then our equivalence is equivariant with respect to this action. So we have some control of what happens with standards on the coherent side. This is going to be important. Questions? Okay, so before we get to a break, I want to talk about some ideas of this proof. And essentially, this comes in two parts. And the first part starts with an observation that our functors are faithful, but they don't need to be full. Nevertheless, we can consider the full images of this functor. So I just take, the full subcategory, which is generated by the objects in the image. Okay, and let me call this full images. And if I want an equivalence satisfying the commutative diagrams that I've written before, here I definitely should have that tau intertwines these full images. Otherwise, I won't be able to get this commutative diagram. Okay, so what we need to do, we need to give a description of these full images. And the description is as follows. So the full image of the constructible guy are all objects which are obtained by convolving with this sheaf. What do I mean by this? Well, remember the equivalence tau was a bimodular equivalence. We have a fine category acting on the left and a fine category acting on the right. So this is a guy living in the category which acts on the right. Okay. So the image of phi2 are these convolutions. The image of phi1 are convolutions like so. So we have Z, which maps into n tilde p. And then I take a fiber product of two copies of Z over n tilde p. And take the structure sheaf with, surprise, surprise, some line bundle twist. And then everybody in phi1 is this kind of convolution. Well, then I need to take Karoubian completions of these two things. So they are prior image Karoubian, and these things are Karoubian. All right, but then I know that these two fellows live in equivalent categories. Again, equivalent via this Bezrukovnikov's equivalence. And you can guess what happens next. I need to prove that Bezrukovnikov's equivalence sends this constructible guy to the coherent guy with a shift. Namely, well, I mean, this should be perverse, and this is just an object in the heart of the T structure, coherent T structure. So this proves that tau intertwines the full images, and if phi1 and phi2 were full, we would be done. The functors phi1 and phi2 are not full. However, what one can show is that they are both T-exact with respect to perverse T structures. Well, that's fairly standard for phi1, phi2 as a constructible functor, and for phi1 you need to prove this. And then you can show that there are full embeddings on the hearts. So the failure of these functors to be full is only in higher axes. So on the hearts, there are full embeddings. And so what this gives us, together with the previous step, is that the hearts are equivalent. Okay? So I have a diagram similar to here, where I need to put perverse shifts on the left-hand side and perverse bimodules on the right-hand side. And then I will have my equivalence and commutative diagram. However, what you can further show is that these triangulated categories actually derive categories of their hearts. That's standard for the constructible category, and actually comes as a consequence of the full package for the coherent category. Okay? So I get my equivalence, which makes the diagram above commutative and satisfies property 1 and property 4. So property 1 is commutative diagram, property 4 is T-exactness. And then we do a bit of work to check the remaining two properties, the equivariance property and the image of the object. Are there questions?
Maybe I can make a quick comment. So you just demystified a little bit. So you said it's not faithful, but it's easy to say how not faithful it is. You just multiply Holmes by some cohomology.
How not full?
Huh?
How not full?
Not faithful, right?
Full. Faithful is injectivity and full is subjectivity.
Right. No, so that basically when you pull back, you change Holmes, but you change them in very controllable way.
Right, you essentially multiply. Right, so what's going to happen? It's still no, it's still full. It's
okay, but
so what's going to happen is this. So how do this? So how does this work? So you can you have left adjoint functors of both phi1 and phi2. And when you compose, going down and then going up, then what you get is not the identity functor, is the identity multiplied by the cohomology of P mod B. Okay? And when you go up then down, then you get convolutions with the objects that I've mentioned.
But basically, since H0 of P mod B is one dimension, right, then on abelian categories you get the same.
Yeah, that's essentially this. Yes. All right. We can have a break, and then I believe Romo was going to make some announcement. Is correct?
Yeah, no, not an announcement. I just wanted to add a comment on my previous talk. And so it was, at some point I mentioned what I called Bernstein presentation for the affine break group. I just want to say that this was inaccurate because what I had in mind was Bernstein presentation for the affine Hecke algebra. That's how it's usually called. So you can generate the affine Hecke algebra by Ts alpha for finite alpha and then theta lambdas. But there is also this fact that I was actually referring to, that the same elements generate the affine break group, and one can actually write a presentation for that, for those generators. So basically, to this, you have to rewrite the relations for the affine Hecke algebra in some multiplicative way, and there is a kind of neat way to do that, and that turns out to be a presentation for the affine break group. And as far as I know, Bernstein has nothing to do with that. So that fact appeared in George Lustig's papers from 83, and then again in more detail in 89. And I personally learned it also from him. But so that's, yeah. So again, I mean, Bernstein thought about affine Hecke algebras and presentations for them, but that presentation for the affine break group, which also plays a role here, is due to Lustig. This attribution was inaccurate. Thanks. That's all.
Okay, let's take a 5-minute break.
Actually, I had a question about the proof, Ivan.
Yep.
So you were describing how to deduce this parabolic version from the kind of Romans version.
Mm-hmm.
But I just want to check. So if you just wanted to prove the parabolic equivalence, like not the compatibilities, could you just sort of run his paper again, but with Johor replace like Perhoric everywhere, or would there be actually some issue?
Can I run Roma's paper? I personally cannot.
But I can, maybe, but well, let me answer related, but not exactly this question. So one can try to do a different thing, which actually we did try in the beginning, that also kind of deducing it, but doing some sort of descent, right? So basically you have, maybe from some perspective, it's more would be better not to use this T structure explicitly, but just say that, well, we have this, well, in this square that Vanya wrote, I mean, you have comparison of the bigger categories, and then you want to deduce the comparison of smaller categories because you can compare this monads, you can compare the composition of the function adjoint, and it should work this way, but I'm just so one needs to work with some derived geometry or homotopy algebra because these functors are very much not exact, so it's all in triangulated categories. And to my surprise, although this seems a rather basic kind of example of this, to my surprise, my friends who know more about homotopy algebra said that this is like hard. Basically, you need to compare, I mean, you have to construct an isomorphism of monads, but like as monads in this homotopy world, and it's very easy to sort of see the functors look the same, but well, we found at least it's easier for us to work with these T structures.
Because at the end, T structures is what we need.
Yeah.
Okay, but yeah, I'm just kind of curious. Like, if you try with a Perhoric that's not the Johori, where do you first get stuck? I mean, you still have this central functor and so on.
No, I think the Again, it's not a monoidal category, but yeah, but if you, it might be possible to just do it that way, but it would be, I mean, this is a much shorter argument here, rather than redoing the work. You can just refer to it.
Ivan, you were saying that it's important that the original equivalence is a bimodular equivalence, but where did you, so you certainly use that it's a left module equivalence in this proof?
I use that it's a right module equivalence. So the proof only requires this to be a right module equivalence, but then you kind of, the applications require it to be a left module equivalence.
Mm.
So right module equivalence is used here. So this whole story is a consequence of the coincidence of full images is a consequence of being a right module equivalence.
Okay, thanks. Yeah, it's been 5 minutes, I think, so we can start the second half.
All right. So we have this theorem. We have this equivalence, which is T exact for Perversity structures. And for our final purposes, we don't need this full equivalence. We just need to have a quotient factor from a constructible category to some, you can say, easier coherent category. And so let me talk about that. So that's about the quotient category. As Roma mentioned in his talk, both category on the constructible side and the category on the coherent side will come with filtrations. And on the constructible side, the index by two side itself, well, since we are in parabolic world, not all cells are going to appear. On the coherent side, the filtration is indexed by important orbits, and again, not all important orbits will appear. And what we want to look at the top quotient of the coherent category, which corresponds to the largest important orbit which will actually appear. So let me explain what important orbits are relevant. So first of all, we consider the open G orbit in n tilde p. Okay, there are finitely many orbits, so we'll take the open one. Well, I mean, there is an open orbit, and it covers some important orbit, which I will call O sub p. Okay, it's the image in G-star. There is a classical description of what orbit you get, that's so-called Richardson orbit for the parabolic P. Namely, you take a generic element in the annihilator of P, and then you take its G orbit. Okay, so this is our OP. And O prime P you can also describe. So you that's a space of cosets of G by the centralizer of E in P. Okay, OP will be the coset space for the centralizer in G, and then the cover will correspond to this finite index sum. Okay. Now I work with this derived stack, and one can simplify it. So it's just the quotient of the Springer fiber, which is formally defined like so, by the action of the centralizer in the parabolic. Okay. So the top quotient of my coherent category is just the equivalent coherent derived category of the Springer fiber, and the equivariance is with respect to this group. Okay, the centralizer of E in P. It inherits a T structure from the entire category. And if you think a little bit about the situation, so this guy will be equivalent to derived categories of modules, so to derived category of this guy. Okay, I take the fiber of A at E, I denote it by A sub E. The centralizer of E still acts, and I consider the category of equivalent modules. And take derived category, it's equivalent to this. And then you can see that these T structures match. Okay. So what do I get? We have a T exact functor going from well, I mean, it's just exact forbidden categories. So we started the category of constructible Perversity shapes on flex of P. And we just get to the category of equivariant modules over this finite dimensional algebra. So all kind of perverse modules are gone. It's just the usual modules. Okay. And we can say what quotient it is. It's a top cell quotient. So inside, I have labels inside of this category. I have perverse shifts which correspond to labels in the two-sided cell corresponding to Richardson important orbit. In fact, they will form a left cell. And I have this top cell quotient, which turns out to be equivalent to this category of modules. Questions?
I'm a little confused about this top cell quotient. What do the cells, the parabolic cells, look like?
So that's going to be the cell of the longest element in the parabolic subgroup.
I see. So you take the longest element of the finite wall group for that parabolic, and then you look at its cell inside the affine wall group.
Yep. And it's going to be so formally I will be looking at the intersection of the two-sided cell with the subset of labels here, but that's a single length cell. So this is kind of, this should be thought as a parabolic category. Okay. And again, the remark, so we had these two additional properties, equivariance and description of the image of the skyscraper. And it still allows us to control what happens with images of standard or co-standard objects in this category of equivariant models. All right, now let me talk about applications to modular representations. So this is kind of, this conclusion is what is essentially used for the application. The conclusion and the remark.
Can I just, so like, I remember how the original theorem was proven when P equals B, this top cell quotient is utterly trivial, of course. But then, so this seems like a significant upgrade, being able to work with these other cell quotients. Is the proof
right? And this is why you need the parabolic stuff.
Yeah. Is the proof much harder as a result, or is it?
No, I mean, the proof of this application is essentially immediate if you know the theorem and its properties.
Can I ask one more question about the last theorem? So basically, in the cell, the Duflo involution should be given by the longest element corresponding to this parabolic, right?
Mm-hmm.
So do you understand what the image of the Duflo involution is? Like, I mean, what the corresponding to the perverse sheep on the left, what's the image on the right? Do you understand this?
We understand well, I mean, okay, so there are several layers of answer. So first of all, we can describe what's going on the level of coherent shapes. So you take this Z diagonal and you intersect with the Springer fiber. What you get is some distinguished component of the Springer fiber. which is essentially all barrels which are contained in the parabolic. Okay, so that's a component, and that's what you get as a structure sheaf on this component. And then when you do modular representations, you can explicitly describe the corresponding object under localization under the global section factor, which will be a certain induced model. So these folks are going to appear in the variant. So there is no separate language to discuss modules over this algebra somehow. You can either discuss coherent sheaves on the Springer fiber, or you can discuss what happens after you reduce mod P. Okay, does this answer your question?
Okay, yeah, thanks.
All right, yeah. So we pick an algebraic closed field F, and for main results, the characteristics should be huge. We had our important element that was in our story Richardson important element, and we can assume it's defined over the integers. We can then reduce it mod P, and we can consider this algebra with a bunch of super and subscripts. So that's a principal block. That's what 0 is responsible for. Or the epicentral reduction of the universal enveloping over F at our important element. Okay. And the connection to the previous story, the basic connection is the result of with Rukavnikov and Mirkovich, is that the ANSI Springer is defined over some finite localization of Z, and you can just say which localization. The fiber at my important element E of ANSI Springer is Morita equivalent to this principal block. So I can, relate, since my the assumption that P is very large comes into play when I want to say that the representation theory of this algebra over F behaves in the same way as the representation theory of the corresponding algebra over the complex numbers. What we care about today is the case when E is distinguished. So let me finally give a definition. It just means that an important element is not contained in a proper layer. Or equivalently, the maximal reductive subgroup of the centralized is finite. And let me give it a name. Let me call it gamma. It's just the same as the component. Let me be user-friendly and show you an example. So let's take G equal to SP20. Well, in this case, important orbits are still classified by their Jordan types, although not all types can appear. You can say which can appear, but it's not relevant. In this language, distinguished corresponds to the condition that there are no repeated parts in the partition. Okay. For example, this is distinguished. 2, 4, 6. 2, 4, 5 is not distinguished. And we can completely describe gamma for distinguished elements. It's isomorphic to Z mod 2Z to power equal to the number of parts. Okay. So that's quite explicit. And then we have the following classical fact. If I have a distinguished element, then I can find a parabolic P such that first, my distinguished element is Richardson for that parabolic. And second, the centralizer in P is the same as the centralizer in G. That's very important condition. So the thing is that every distinguished element is even, and for every even element, you can write down this parabolic. So what do we get? We now get a description of modules over A of E, that's a finite dimensional algebra, which is equivariant with respect to this group. This group is an algebraic group, but its reductive part is finite, and everything else is unipotent. So we have description of this category as the top cell quotient of the parabolic of affine category. what do we do with this? First, let's make a couple of observations. So the centralizer of E is finite times unipotent. And unipotent doesn't affect K-theory. So this equivalent K-theory that we know, it's a left cell module, is equivalent K-theory of this guy, which is finite dimensional algebra. And then you take modules equivalent with respect to a finite group. This category, this numerics are not going to change when you reduce mod P for P very large. Okay, it's just the same case theory over F as it was over C, which is written here. And then it's an isomorphism of base abelian groups, where I consider basis of simples. So, you know, now we have information about simples in this algebra. This just because they just correspond to Kazhdan-Lustig basis in a certain cell model. And I told you the result of Bezrukavnikov and Mirkovich that this the category of usual modules are Morita equivalent. You can show that the same works for equivalent modules, which shouldn't be very surprising. Okay, so what I get a description of simples in the category of gamma equivalent modules in the principal block of representations with P character E. Are there questions? So that's nice, but it's not complete happiness, because if I want to write character formulas, I cannot just say that I have a, you know, I know K-theory as a module over something. What I need to know, I need to understand standard objects, in terms of which I'm going to decompose my simples. And in some settings, standards form a basis in K-theory. In our settings, they will form a spanning set. And of course, the standards will be images of standards from the affine parabolic category. So I need to give some representation theoretic description of these images. And it turns out that this is possible to do because of those additional properties of the parabolic equivalence that I haven't used as of yet. So let me explain details, which is going to be a bit technical. So, K-theory that I care about, this equivalent modules, is the top cell quotient of K0 of Perversity shifts, and of course I know what it is. With my conventions, it's induced from the sign representation of the finite parabolic Weyl group to a fine Weyl group. So W semi-direct with characters of the torus. And this is W super A, W sub P is this finite parabolic corresponding to P. And then here I have standard basis, just basis of group elements, which kind of survive nicely in this module. And I want to understand the images on the representation theoretic set. And it turns out that they are classes of certain induced modules, as I mentioned. Now, what elements of the affine Weyl group should I take? These are elements which are longest in the right cosets with respect to W sub P. Okay, they will correspond to a basis in this model and to a basis of standards. Now, I want to describe where they go in this case zero. So that's going to take a little bit of time. First of all, the fine while group, of course, acts on the character lodges in the standard way. So I have the dot action on the finite part, and then I have rescaled translations on the lattice. That's very standard. And then I take a levy inside of P, and I consider its character sub x given as follows. So I take -2 row, and I apply element x minus 1. So x is going to live in here. So when it lives in WAP, this longest positive representative, it turns out that mu sub x is dominant for L and vice versa. So I have a so each element of my label in set gives me a dominant weight for a levy. What can I do with a dominant weight? I can form a highest weight module with this highest weight, and I'll take a while module denoted by such W sub LF. Okay, that's a module over L. In particular, it's a module with trivial P character over the Lie algebra. Okay, but also with this yoga of distinguished important elements and parabolic subgroups, you can actually arrange that gamma lies inside of L. So this while module is going to be over U0F, and actually it's going to have trivial horizontal character. Things I can induce from equivalent modules here to equivalent modules in the algebraic parabola, which is this one. So how do I do that? I notice that the P, this restricted universal enveloping algebra for P, is included into the non-restricted universal enveloping algebra for G, because E vanishes on P. And it's actually, as usual, a free module. So the large algebra is a free module over the small algebra of this rank. Okay. And then the final proposition for today is this. So the class of standard labeled by X, so X lives in here, goes to the class of this module. So it's not true on the level of modules, it's true on the level of K-theory classes. And this is the module whose character dimension is very easy to compute. You have wild dimension formula on this factor, and then when you pass to induced module, you multiply by this. Okay? So I have this bunch of standard modules whose dimensions I can compute. And I know that the coefficients of simple modules inside of this are just parabolic of anchored acoustic polynomials evaluated at 1. And so I get my character formula and my dimension formula. All right, that's this is the end of this talk.
Any questions for Ivan?
Okay, can I ask a question?
Sure.
Okay, so one for the distinguished, so you have a distinguished and important. So do you? So which left cell are you using? Are you using a particular left cell for?
That's right. That's the left cell which corresponds to the longest element in the parabolic subgroup.
So you say this element is induced from some. Okay. Okay. That.
Right.
Okay.
So the distinguished element gives me parabolic subgroup.
Okay, but then there is a second question. Well, since there are now these two versions of this character of this, but this one you describe, and this one of the Mirkovic, which is a different one. But this suggests there should be some connection between the left cell and this canonical basis. Should be some.
Right.
Okay, do you understand what is the connection? There's some kind of correspondence, not bijection, or almost bijection, but not quite.
Right. So an important thing to mention is that we are living in different categories. So
No, I understand, but yeah, because so in one case it's some equivariant representations, and the other case not equivariant.
Right.
But these are still not related. There's some relation between them. You can forget the equivariant structure or something.
Right.
And so you should get some connection between this left cell and the canonical basis.
Right. And this is subtle. This is subtle.
It is what?
This is a subtle question.
Okay.
So although the group is, you know, this group is usually very easy. It's
I guess the discussion is subtle, but there are some easy things you can say, right?
Okay, shall I try to say them? Right, so the way how you could think about it is that you have a finite set of irreducible representations of this algebra. So let's say this algebra, if it's modular counterpart. And then on this finite set, you have an action of gamma. Now, the thing is that this is not just a set, it's centrally extended set. So points will come with Schur multipliers. And the fact is that some of the Schur multipliers are non-trivial. That's this is known for a fact. In fact, for some nilpotents, it's possible to count how many elements have which stabilizer and which Schur multiplier. And because of this kind of Schur multiplier business, it's so one could ask this phrase the question is like, okay, so I'm given an equivalent reducible module, can I decompose it into usual irreducibles? And the presence of the Schur multipliers makes things complicated. So that's the principal complication to go from the equivariant category to non-equivariant category.
No, but still there will be, maybe it's up to introduce some scalars which are subtle, right? But
right, so scalars in this case are going to be powers of 2.
But up to scalars is just the average of
right. So you kind of, what's going to happen is that, so a simple in the equivariant category is kind of is a simple, corresponds to a simple equivariant sheaf on this finite centrally extended set, and then one should try to compute the fiber and one should try to compute the orbit. And somehow, currently it's unclear how to do this.
But for example, in one example, if you take subregular nilpotent in E8, then this left cell and the canonical basis are actually canonically in bijection. So that's in that case.
Right. I think subregular cases are easy, and difficult cases are those kind of in the middle.
Okay.
So I guess in the subregular for E8, this group gamma is trivial, right?
Yes, yes.
So then there is no complication.
Right. If gamma is trivial or gamma is Z mod 2Z, or maybe S3, then there are no cycles, but starting from Z mod 2Z squared, there are, and makes life complicated.
But still, I think this still suggests that I think there should be some relation between, if you know all the left cells, you presumably can reconstruct this canonical basis from all the left cells.
This
I will imagine.
it's not quite clear to me what one needs to know in order to do the full reconstruction. It's kind of.
Okay.
It's possible that, you know, if you know the asymptotic Hecke algebra is a based algebra, then maybe you can reconstruct everything completely, but even this is not obvious.
Sure, but what is exactly the equation? So it's looking at other left cells.
So I give you an element of a fine Weyl group in a given left cell. Okay, so this gives me an orbit in this finite set with central extensions. So can I determine this orbit and the Schur multiplier for the stabilizer?
I guess, yeah, it's an orbit on the square, right? Elements in the affine Weyl group.
No, I'm in a left cell, so it's just one orbit, just one copy. So what does one need to know to get from non-equivalent category to equivalent category to non-equivalent category? And I don't have a very clear answer in my head for this.
Okay.
But I don't think we have a good understanding of this, what you call Schur multipliers. I mean, we know they're non-trivial in some examples, but.
Right, so in some, so I have a graduate student whose name is Kian, who's here. So he's working on doing counting. So, you know, I give you a distinguished nilpotent in a classical group, for a classical group. And you need to tell me how many of given orbits with given Schur multiplier are there. And for some important elements it's possible, and for some others it's work in progress. But it doesn't answer the question, because the question is, I give you the data is different. I give you an element in a fine Weyl group. Okay, and then ask, well, what happens for this particular element, and not just how many elements of a given type are there.
Mm-hmm.
That's a different question, and there was another one.
So again, for example, if this gamma is trivial, then you just need.
There is no question.
There is no question.
If gamma is Z mod 2Z, I think this shouldn't be hard. If you know all the multiplicities of intersections of all left cells and all right cells, number the element of intersections. But beyond that case, it's sort of difficult.
I guess another natural question is, how do you, what happens when you try to get rid of the for large P statement?
So, okay. You can ask this in two versions. You can ask this for distinguished element. You can ask it for general element. I believe that for distinguished element, it will just boil down to the correspondence story about Hecke categories. So you may need to replace cells with P cells, and you may need to replace cardanolistic basis with P cardanolistic basis. And apparently the modular version of the full two realization equivalences in the works. One could argue that perhaps one could deduce the parabolic version in a way similar to what we've done. And then you have this quotient category, and this kind of story. So for distinguished element, at least under very modest restrictions on P, the answer should be the same. There's a more interesting question of what happens when the element is not distinguished. So I wasn't asked about that, but maybe I can still talk about it for a little bit. So when the P character is not distinguished, what we get with Roma is a statement on the level of case theory, which essentially uses Bezrukavnikov and Mirkovich theorem about causality for this algebras. Certainly, causality is gone in characteristic P. And also, there is a suspected version of a categorical statement, which is, okay, so in order to prove our case-theoretic statement, another ingredient is some stabilization for cardanolistic polynomials. So if you take two elements in the affine Weyl group and shift it by a translation which is sufficiently dominant for the parabolic, you translate by a character of this parabolic which is sufficiently dominant, then the cardanolistic polynomials stabilize. This was first obtained by Stropel in her master thesis. You can ask a question, is this true on the level of categories? So, you take a finite interval in the Breuer set. You take the corresponding subquotient category in the affine category O, and you shift it up. You ask, does the category stabilize? And I think the answer is yes for strictly dominant elements. Is this so? Okay, Georgia thinks this is so.
I think that this is not so mod P though. This is definitely not the case mod P.
Right, but even the parabolic version is not known, at least to me. And what happens mod P is, well, you know better. So it's not quite clear what even to expect from non-distinguished elements.
Can I ask about what you said, but about the first part of about the distinguished case? Suppose even like stabilize is trivial, so that there is an exact kind of comparison between cardanolistic base.
You froze for a minute.
Hello?
You froze for a moment.
Ah, sorry. Yes. So suppose we can express this canonical basis in K group of the Springer fiber in terms of the cardanolistic basis. But then you're saying that for specific P, we'll get this P cardanolistic basis, right?
Well, this is what we could expect.
Yeah, but that's actually, I kind of, I agree it's a natural guess, but it never occurred to me to investigate this. And So I don't know. Should we expect a P version of the canonical basis in terms of George's definition from this? In terms of the definition that we worked with Merkovich.
Well,
perhaps not because
I
of positivity.
No, because that's a case-theoretic statement. And,
yeah.
So kind of.
So I guess it'd be interesting to even define. So it looks like there is some definition in this case, but it would be interesting to.
Right, but deterministic basis are not defined at the level of modules,
basis right? in the K group of this string file.
If you want to define them, you need to kind of have a category which you believe you understand. Or at least you declare you understand.
Before, I mean, for a few years after the project with Merkovich was done, and before we started this work, I thought I understood these categories, but now, I mean, that has been ended. I mean, you overturned this conviction when we started.
Well, you provide bad publicity for me, you know. Really want to collaborate with people that so that after you collaborate, you understand more.
Yes.
Right? And nobody wants to collaborate with people with whom you understand less.
Just a comment is that I remember in one of my first conversations with George, he told me that we don't understand these bases in K theory of Springer fibers.
Well, I agree.
But I think I understand them a little better than at that time.
That's good. Yeah, it will be
because there is, I think I can define at least conjecturally what is standard basis, not only canonical basis, but standard in the K theory of Springer fiber. There's also something like standard basis, and that should be helpful to understand what's canonical basis also.
Any more questions or comments? Okay, if not, let's thank Ivan again.
Okay, Mackie, can I just briefly, I posted at the very beginning, but I think that's before actually I did this unstrategically because we're no longer at max capacity, so please register for the conference next week if you haven't already done so, and you would like to attend at least one talk. And also the time that I just downloaded the calendar thing from the website, and it just does a generic like 8:30 to something time. So don't download the calendar and look on the website for the schedule.
So this was the last talk of two realizations series, and I guess a lot of people have already left, but I'd like to thank all the speakers.